Alright class, we're looking at an old test for test 2, and we're going to start with the multiple choice. And the first question says, carboxylic acid can be reduced to a primary alcohol via which reducing agent? And it gives us some options. It gives us borohydride, lithium aluminum hydride, sodium borohydride, and D, the lithium aluminum tritert butoxide hydride. And the correct answer here, I think, was a mistake on the test, but anyway, the correct answer is A and B. Both of these reagents will reduce a carboxylic acid. All right, so you could, I guess, choose either one. All right, 2. A good method to prepare a carboxylic acid from a nitrile would be, well, if you have a nitrile and you treat it under acidic hydrolysis, so a lot of water and acid, and heat it, you can get a carboxylic acid. And so that's going to be A there. Choose the correct functional group name for the following. Okay, the following is a cyclic ester, and that is called a lactone. 4. List the following in terms of increasing boiling point, assuming they have about the same molecular weight. Okay, well, I have a choice between an acid, an amide, an alcohol, and an ester. All right, so the highest boiling point is going to be the amide because those have those resonance structures where they have full charges on there. The carboxylic acid is going to be the next highest because of its strong hydrogen bonding, and then the next highest with hydrogen bonding is alcohol, and then with no hydrogen bonding is the ester. So the order is going to be D, C, A, B, which looks like it's C. 5. List the following in terms of increasing carbonyl stretch. Okay, so what I'm going to do here is I'm going to say, well, I know that acid halides are really high, and I know that amides are really low. So from increasing, I got to go from C at the end to B at the end. And I'm just, oh, look, there's only even one option that does that. So I'm going to say there's D. Yay. The other guys are in the 1700s. Choose 6. Choose the least reactive of the following for nucleophilic attack. All right. Well, we have an acid, we have an acid chloride, we have an amide, and we have an ester. And for all the acid derivatives, we know that, for example, acid chlorides are more reactive than an ester, which is more reactive than an amide. But carboxylic acids in particular are really not very reactive for nucleophilic attack. As a matter of fact, you got to turn it into the carboxylate anion before you can turn it, have a nucleophile attack it, because it just is an acid. It wants to do acid-base chemistry. All right, number 7. List the following molecules based on increasing pK of the bolded hydrogen. Okay, this is a alkane, so that's about 45 to 50. This guy's an aldehyde, so about 20. Off of an amine is about 35. This guy, remember, was like 11 or 12. So, something like that. So, the range is going to be A, increasing pK, increasing D to A. So D to A, I have 2 of those. And then it's going to be D, next highest, C is the next 35, and then B. So the order should be D, B, C, A, which looks like it's B. All right, identify which intermediate is not present during the Stork enamine. So we know that we get an enaminium salt, an enamine, a carbanolamine. We get all of those things. What we don't get is an enol, because it's not enol, it's nitrogen chemistry, so D. 9. The following reaction is an example of, all right, so there we have our malonic ester, and so that's going to be a malonic ester synthesis, so that's D. All right, page 2. Which of the following would be a poor Michael acceptor? Remember, to make a Michael acceptor, what we need is an electron withdrawing group off of a pi system. So a nitro group, an aldehyde, an ester, all of those are good electron withdrawing groups. The methyl is actually an electron donating group, so we wouldn't want that. Which of the following is false about fructose? Fructose is a hexose. A, it is a ketose, that's true. B, it is a hexose, that's true. C, it'll form fructopyranoses. No, it forms furanoses. So C's false. And is a monosaccharide, that's true. All right, please name the following. All right, the first one that we got to name is an ester. So we got to name the R group first. So that's a benzyl group. And then I'm going to number, this is going to be the O8. So it looks like a pentenoate. So it looks like 4-methyl pent 2-ene O8. All right, this is an acid. It's got a cyano group, and this guy, that's a methylpropyl group. It's an octanoic acid. The cyano group is going to come first. I got to do the stereochemistry here. This is going to be 1 because it has 2 carbons. This guy will be 2. This guy will be 3. So that looks like S to me. So that is 8 cyano, 3 1-methylpropyl, octanoic acid. All right, then it wants us to draw a lactam. Now we know a lactam is a cyclic amide. All right, it's telling us we got 4 carbons in our ring with the nitrogen. So I'm just going to draw that. Here's my nitrogen, and then I got 2, 3, 4 carbons attached. Okay. And then it tells us that on carbon 3, I have 2 methyl groups. And on carbon 4, which is this guy, it's got that amino group with a propyl. So I'm going to put that guy on there. And so there's our lactam. All right, we're going to turn our attention now to fill in the blank. All right, we've got an acid. We want to turn it into an acid chloride. So that's either going to be thionyl chloride or oxalochloride. Oxalochloride. That is so not oxalochloride. There we go. All right. That's an ore, right? Oh, sorry. Oxalochloride is not that. 2. There we go. Okay. All right. Then the other one, we got a Gilman reagent. So the Gilman will just go and do the coupling reaction to make that new carbon-carbon bond. All right, we're going to nitrile there in B, and we're going to reduce it. That will not affect the double bond, so do not reduce the double bond. Just reduce the nitrile group to an amino group. Then we got an amine. I'm going to treat it with acetic anhydride, and when I do that, I'm going to make an amide. All right. And then if you let's see, we got an acid, and I'm making an alpha bromo acid. So that sounds like a Hell-Volhard-Zelinsky reaction that then has been treated with acid. To turn the acid bromide back into the acid, the carboxylic acid. Then we're going to treat that with diazomethane, so we're going to make the methyl ester. And then, so the intermediate here is going to be a methyl ester. And then we're going to treat that with Grignard reagent, which will add twice to that carbonyl. So that guy will be an alcohol now, and it'll have 2 of those carbons attached. All right, we're going to take an amide, and we're going to dehydrate it, and that is our way to go to a nitrile. Then we're going to take our nitrile, treat it with a Grignard reagent, and work that up. That's going to get, remember, an enamine, which will then hydrolyze to the ketone. Oh, sorry, imine. That will hydrolyze to the ketone. All right, E, I've got something blank, and it says I treat it with LDA and benzaldehyde and acid workup. Ooh, it looks like I'm doing an E2 here, so let me think backwards. That would be an alcohol there. So I'm going to draw that. And just to save room, I'm going to call that a phenyl group. So that is this starting ketone right here, which then I form the anion on, and that attacks the aldehyde carbon and gets us that alcohol. All right, F looks at acetoacetic acid synthesis, and so acetoester synthesis. And so what we're going to do is we're going to treat it with one equivalent of the ethoxide. We're going to go and do the SN2. Then I'm going to go, let's see, what did I add here? Looks like I added 1, 2, 3, 4 carbons. So once again, treat it with one equivalent of the base. And then those 4 carbons. So I'll just do a bromine. Let's see. And then I got to work it up with acid and heat to do the decarboxylation. So hydrolyze the ester to the acid and then decarboxylate the acid. All right, next. Short answer. Number 1, a freshman student in Chem 145 left the cap off of a bottle with a small amount of acetic anhydride open for the weekend. The IR, the remaining residue, showed a very strong broad peak centered around 3,000 reciprocal centimeters or wave numbers and a strong peak at 1710 wave numbers. What happened? Write the reaction. Why does this reaction happen so easily? All right, so we've got acetic anhydride, and we've left it open to air, which has got water in it. And unfortunately, when we did that, remember, acid chlorides and acid anhydrides will go and hydrolyze very readily. So acid anhydrides and hydrides hydrolyze readily. All right, and so then we're going to get our OH stretch for the carboxylic acid about 3,000 reciprocal centimeters, and it'll be very strong and broad. And then we're going to get the carbonyl stretch for the acid at about 1710 centimeters, and that should be strong as well. All right, number 2, finish the following reaction and then give me a mechanism. So what we're doing is we're taking an acid chloride and an amine, and we're making an amide. All right, so it says we've done that with a little bit of extra pyridine instead of just extra dimethylamine, which is fine. Most of us would have just used extra dimethylamine, but anyway, we're just going to attack. When we do that, we're going to get the O-, we're going to get the Cl, we're going to get the nitrogen, it's going to be charged. We're going to close back down, we're going to kick out the chlorine. Now we don't want the chlorine to come and attack and make HCl gas because that's really highly toxic. So that's why we're going to either have some extra methylamine or we're going to add a little pyridine to go and pluck off that proton. So, so that does definitely not charged. But that's going to make that pyridinium salt, which will be charged. It's going to be balanced by that chloride there. Okay, number 3, they're giving us a target molecule, so we got to figure out how to make it. So it says remember, this is the starting material on this side of the arrow when we're doing retrosynthesis, and this is the product. Okay, so we want to go that way. All right, so looks like we had, if I can think backwards here, I'm going to just make that guy a carbonyl, because I can take a carbonyl and treat it with a Grignard reagent and make that tertiary alcohol. So if that's a ketone, that's an alpha, beta, unsaturated ketone. And we know that that is a product of an aldol. And that makes sense. I'm going to take an aldol, I'm going to take a ketone, I'm going to do a crossed aldol. Okay, so I've got to figure out which one I'm going to use. I've got to add essentially a benzaldehyde, a benzyl group. So I'm going to use benzaldehyde. So okay, and then we'll worry about that later. Oh, we probably need a Grignard reagent from that. So the Grignard reagent, since we added a methyl group, I'm going to need the Grignard reagent. So thinking backwards, I need methyl bromide. Okay. All right, so let's go. I'm going to start with make my Grignard reagent. I'm going to take my ketone. I'm going to treat it with LDA or hydroxide. I'll just do hydroxide because I'm going to need to do the saturation, the E2 later. That will go and that will react with my benzaldehyde. I'm just going to write the benzene ring as a phenyl group. And then, of course, I can heat that with hydroxide, and that will do the E2. To get to my ketone product. And then I can treat that with one equivalent of my Grignard reagent, a little bit of acid workup, and I can get to the target molecule. Which, of course, reacted with the ketone. And so I get an OH. And then I get that methyl group added. Okay. All right, let's see. Going on to the last page, we've got, it says, we've got a Claisen condensation, so that's esters reacting with each other, followed by a Robinson. And Robinson is always a Michael, and then an aldol. So we're going to do the Claisen condensation first. They're going to go here and make the enolate. The enolate is then going to attack that ester. And remember, this will be a leaving group and leave. So, because it does acyl substitution chemistry. So I'm going to get that 1,3-dicarbonyl product, which is very common for Claisen and cross-Claisen reactions. Then I don't know what I'm doing because it says do something, get to B, which we don't know. Use hydroxide, get to C. C, we're going to heat and dehydrate. Okay, I can play the dehydration game because remember, wherever that double bond is, on the beta carbon, put the OH. So C must be whatever this mess is with a OH right here. Okay, and then if I think backwards, all right, this is the carbonyl carbon right here, so there it is. So I must have attacked both there. And then if I think about, you know, the hydroxide would have allowed that attack. So I need this bond to be made in B. I need this bond to be present in B. So let's just disconnect where that red line is and draw what we got. So I've got my, back to my ketone, because it hasn't reacted yet. It has this guy attached to it. Okay, and then I've got that bond, that bond, that bond, that bond. Okay, so if I go here, I got 1, 2, 3, 4. 1, 2, 3, 4. All right. So how can I add those 4 carbons to this guy? Well, that looks like it. Once again, we know it's a Michael. This is the aldol part. This is the Claisen part, right? So the part that's missing is the Michael addition. So for the Michael addition, I just need an alpha, beta, unsaturated ketone in this case with 4 carbons. 1, 2, 3, 4. Okay. Why do we see regioselectivity with B with base? It's got a bunch of carbonyls. It's, it could form this anion, it could form this carbanion, it could form this carbanion, it could form that carbanion. What we want to see is we want the primary carbanion will be formed first because it's the lowest energy. Okay. Please answer the following questions concerning D-galactose and circle the correct vocabulary. So this must be D-galactose over here. So I go and I count and notice that I have 6 carbons, so it's definitely hexose. It's got an aldehyde functionality, so it's an aldose. It's a reducing sugar because it's an aldose. They want us to draw the C5 epimer, so we're going to leave everything the same. We're just going to, so here's 2 we don't change. 3 we don't change, 4 we don't change, 5 we change. All right, now since that OH group is on the left, this is no longer galactose. So this is an L-galactose. I don't know what this is, but whatever its name is, it's L. All right, because L-galactose would have to be the enantiomer. Everything's switched for galactose. All right, show the formation of the pyranose, the 6-membered ring of D-galactose, and label each ionomer. All right, so remember, the nice thing about this is everything that's on the left-hand side for 2 through 4, okay, these guys, is going to be up in our Hayworth projection, and everything on this side, right, is going to be down. Now remember, carbon 5 rotates, so don't be thinking carbon 5 does that. So this is special. This is the guy that rotates. All right, so I can get my 2 basic drawings here. Here's the beta version. Here's the alpha version. Okay, now let's go and fill everything else in. Everything else will stay the same. So carbon 2, we got to have the H up and the OH down. Carbon 3, OH up, H down. Carbon 4, OH up, H down. So 4 OH up, 3 OH up, 2 OH down. Okay, and then it said label each ionomer. So this would be, this is the beta. So this is beta D galactopyranose. And this is alpha D galactopyranose. Then it says draw the 2 chair conformers for beta D galactose. So this one. And is one conformer preferred over the other? So let's just draw some basic chairs. All right, number 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now let's put it on beta. So beta, we've got on carbon 1 an OH is up and an H is down. And then on carbon 2, we got an H up and an OH down. Our carbon 3, we got an OH up and a hydrogen down. On carbon 4, we got an OH up and a hydrogen down. On carbon 5, we've got our methylene with the OH up and then a hydrogen down. So once again, going back, carbon 1, we got an OH up, a hydrogen down. Carbon 2, we got an H up, got an OH down. Carbon 3, we got an OH up, we got a hydrogen down. Carbon 4, we got an OH up, we got a hydrogen down. Carbon 5, we have the CH2OH group up and a hydrogen down. Alright, so I'm going to go and I'm going to circle the groups that are in 1,3 diaxial interactions. This guy is with that guy and that guy. And then on the bottom, I have this with a hydrogen. Maybe I'll do the bottom in blue. So the bottom guys are in blue. So top 1,3 diaxial interactions, I got an OH, I got an H, and a lone pair. And then on the bottom, I got an H, an H, and an H. Now, we can see in the circled groups that on the compound to the right, we have less bulky groups in diaxial interactions. We only have one non-hydrogen in an axial position. So that means that my 1,3 diaxial interactions are much lower in energy because I've just mainly got hydrogens. And so this is going to be the lower energy, so it's really going to favor making that conformer. And I think that's the end of the test. All right, the old test. All right, take care. Let me know if you have questions. Hang in there.